See, now to understand this question, you must first understand something. Okay. So suppose this is a top, you know, let 2. Okay. And this top spins about this axis with angular velocity omega. Understood? Now just before and this top is spinning on the ground. Okay. This is the ground. Now have you noticed something? Just before the top, stops spinning. Okay. After a certain while, the tops become somewhat like this. See, it becomes somewhat like this, and this top keeps on spinning like this. Okay, and the entire top rotates around this circle, somewhat like this, isn't it? The top spins also like this, the top rotates also like this, just before falling down. Okay, now that exactly is your question. Okay, the angular velocity of top's precision. That means what is the angular velocity in which the top rotates like this? That is the angular velocity of precision. Okay, and the magnitude and direction of horizontal component of reaction force at the topmost point of, okay, see, out here. Okay, the normal contact forces will be there, and since this top is spinning somewhat like this, okay, the top is spinning somewhat like this just before dying. That means the center of mass of the top is also moving in a circle, somewhat smaller circle, but is moving in a circle, isn't it? So somehow someone is making the center of mass move in a circular orbit. So there must be some centrifugal force. Okay. And who is applying that centrifugal force? Normal reaction force out here. Okay. The normal reaction force out here is applying the centrifugal force. Fair and fine. Okay. And since there is normal reaction force in this component, there will be normal reaction force in this component also. The second part of the question is asking find the normal reaction force or horizontal component of normal reaction force. Okay. So we'll begin our journey by first part of the question, the angular velocity of the top's precision. Okay. So before we move on to angular velocity, just recall your previous chapters and tell me what is the value of gyroscopic acceleration. Gyroscopic torque. I have said it repeatedly. Okay, it started at Newton's laws of motion. Torque is equals to I angular velocity of precision cross angular velocity of rotation, isn't it? Okay. Now see, suppose this top, okay, was rotating in this axis just before dying. So the angular velocity of precision would be in this direction. The vector of angular velocity of precision would be in this direction, omega p, isn't it? So let me draw something. Okay, let me draw a axis. Okay, and let me say this angular velocity of precision or omega dash. Okay, omega dash is out here. So let me just bring this diagram a little bit down. Okay, and angular velocity of precision is out here. Okay, and let me say this angular velocity of precision as omega dash, and we have to find out the value of omega dash. Okay, okay, the moment of inertia of the top is given, fair and fine. Okay, so about this point in motion, say I'm taking this is the axis or this is my origin. Okay, if this is the origin, okay, at the instant it is rotating like this. Okay, if I take my torque through this origin, what is the value of torque? Value of torque is nothing but mg into L and this component of L. Okay, so let me say this distance is nothing but L. Okay, this angle is theta, so that means this distance would be nothing but L sine theta. So torque would be nothing but mgl sine theta. Understood? Moment of inertia is already given as I see. The moment of inertia of the symmetric axis equals to 2 gram per this one. Moment of inertia is already given, isn't moment of inertia of the top. And see, what is the direction of torque? If you see properly, mg is pulling this torque in downward direction. What is the direction of torque? Torque is nothing but, torque vector is nothing but along this axis, isn't it? So moment of inertia of the torque along this axis is given, angular velocity of precession along this axis is given, and angular velocity of rotation along this axis is also given. So this is the perfect component for gyroscopic acceleration. Okay, I is given, omega p is given as omega dash, and omega is already given in the question, 350 radians per second. So if I combine all my equations, okay, torque is equals to mgl sine theta is equals to moment of inertia is equals to omega dash into omega, or omega dash, wait a minute, I think I haven't, okay, let me rewrite, mgl sine theta is equals to I into omega dash into omega is equals to how much, or omega dash is equals to mgl sine theta divided by I omega. This is the value of angular velocity of precision. So we find out the angular velocity of precision. Now we have to find out the magnitude and direction of horizontal component of this value. Okay. Okay. Fair and fine. Now let's check. The center of mass of the top is rotating in a circle. Okay. So if I balance out the centrifugal force means how much? Just centrifugal force. Centrifugal force means mg L sine theta. Okay. Okay. Nx, sorry. Centrifugal force is nothing but Nx. Nx is equals to m omega square r. And what is the value of r? The value of r is nothing but this much distance. And this much distance is nothing but L sine theta. L sine theta. What is omega? Omega is nothing but the angular velocity to which the center of mass rotates, which is nothing but omega dash. So omega dash. So Nx would be nothing but m omega dash square into L sine theta. And if I substitute my omega dash from here, I would get, it is nothing but mgl sine theta by I. Now put the values and get the answer. Nx is equals to mgl, or m squared gl, m squared gl square. Okay, so whatever the values, just put the values and find out the answer. Okay, I'm not spoon feeding you the answer. So this is a straight up question from gyroscopic acceleration. Okay, so gyroscopic torque. Torque is equals to I omega p cross omega. Okay, the angle between omega p is nothing but this vector along this direction. Okay, because the wheel is rotating in this circle, isn't it? And omega is nothing but along this direction. The direction between omega and omega p is nothing but 90 degree. So sine theta out here becomes 90 degree. What is the moment of inertia of a disk? Moment of inertia of a disk about this axis, okay, about omega, is nothing but a mass square by 2. What is the torque? Torque is given about which axis? Torque is given about origin. So mg into L. Okay. So mg into L is nothing but mgl, isn't it? Omega p I don't know. Acha, the gyroscopic, acha, 0.5 rps. So if you want to convert rps into radians per second, we just multiply. So omega p is equals to 2 pi into n radians per second, isn't it? Because 1 round per second is 2 pi radians per second, isn't it? So whatever is the speed in rps, you have to convert. If you multiply it by 2 pi, you will get radians per second. Okay, find out the angular velocity. I have to find out the value of omega. Okay, acha, one more thing. This entire setup is kept in an elevator that is moving up with acceleration 2 meter per second. That means this entire setup, okay, this entire setup is kept in an elevator that is moving up with acceleration how much? 2 meter per second. 2 meter per second square. 2 meter per second square. And what do you do when the lift moves up with acceleration A? Everything becomes G effective. That means whatever G I wrote out here, this would become G effective. And when the elevator moves up, G effective is equals to G plus A or minus A? G plus A. So I'll get my equation as M G plus A into L is equals to M R square by 2 into omega P, that is already given in the question, into omega. Okay. So M and M would get cancelled. And what else is getting cancelled? R square by 2, R square by 2. I need to find E. Okay. So M got cancelled. Okay. Let me shift this 2 out here. Okay. This R square out down out here. Okay. And this dash will come out here. Since this dash is short, I'll just erase it and make a new line out here. Okay. Omega P. Omega P is given in the question. Omega P will come out here into omega P. And since I have to find out the value of omega, this omega I'm writing it out here. Okay. So this is my equation. Okay. So the value of L is given. See, the value of G you already know 10 meter per second. The value of L is given 10 centimeter. Convert that is 10 centimeter to meter, 0.1 meter. Okay. A is given as 2 meter. So in this question there is a sphere. Okay. And this sphere is rotating in this direction. Okay. So the angular velocity is in this direction. Omega. Okay. And that omega is given as 1250. Okay. Radians per second. Now see. This sphere is also connected to a rod. Okay. This rod is also spinning or might not be spinning. I don't know that. Okay. And this rod is rotating about this axis. Okay. With angular velocity omega dash. Omega dash 5 radians per second. Okay. The question is asking find the modulus and direction of gyroscopic forces. So obviously if the angular direction of this angular velocity is changing, obviously torque is acting, and we know that gyroscopic torque is nothing but I omega dash cross omega. Okay. What is the angle between omega dash and omega? 90 degree. Omega dash is always in upward direction and omega is this direction in this plane, isn't it? Okay. Fair enough. Now we'll just plug in the values. The moment of inertia for sphere is nothing but 2 by 5 mr square. Okay. Omega and omega dash is done. Okay. Now see this torque. See, to rotate this angular velocity, there must be someone to apply the torque on this system, no? And that torque is applied by a force, isn't it? So I do know that torque will also be in this direction. Okay, torque would be in this direction. Okay, and this torque is trying to rotate the angular velocity omega. So when the ball reaches out here, the torque is in this direction. When the ball reaches out here, the torque is in this direction. When the ball reaches out here, torque is in this direction, means positive z. When the ball reaches positive z, the torque is in x direction. So the torque and omega vector are rotating with each other with 90-degree angle in between them. Okay, and this torque is caused by a force. Now suppose to make this torque, that means this is a clockwise torque, so the direction of force must be downward. We know that torque is equals to L cross F. L cross F. Now if I apply F in downward direction, L is in this direction. Angle between L and F is nothing but 90-degree. Okay, so let's make it that. So LF is equals to omega dash omega. So now everything is solved. LF is equals to 2 by 5 mr square, r square, into omega dash omega. So F is equals to 2 by 5 mr square. Where is the square? I'm just forgetting the square. Omega divided by L. So this is our answer. Just plug in the values. Okay. Mass is given. R is given. Okay. Omega dash and omega are given. Omega dash, omega, and L is also given 15 centimeter. Okay. So this was our answer. Now in this question, there is a ship. Okay. And see, I'm seeing it from the top. Okay. And this ship is moving in a circular orbit. The radius of the orbit is nothing but 200 meters. Okay. And inside this ship, there is a cylinder that is spinning. Okay. The angular velocity of the cylinder is nothing but omega. Okay. This omega is given by 300 rpm. Okay. Now, if I'm seeing from the top of the sea, and if this ship is moving in a circular path, okay, is the direction of angular velocity changing of this bearing? Obviously, when the bearing is out here, the angular velocity is in this direction. Okay. When the bearing is out here, the angular velocity is in this direction, isn't it? Okay. My first question is, if I look from the center, at what angular velocity is the angular velocity spinning? That means initially out here, the angular velocity was in this direction. Okay. When it reached out here, the angular velocity is in this direction. When it reached out here, the angular velocity would be in this direction. Okay. And when it reached out here, the angular velocity would be in this direction. So if you see, the omega is also spinning, no? Isn't it? The omega is also spinning. And with what angular velocity is the omega spinning? Omega dash, or angular velocity of precision. Okay. Now I just need to find out the angular velocity of precision, or with what angular velocity is the omega spinning. See, if omega spins like this, okay, if I say the angular velocity of the ship is nothing but, let's say, 5 radians per second, okay, or just a minute, if the ship completes one full rotation, okay, I can say omega also completes one full rotation. That means if the angular velocity of the ship is one rotation per second, isn't it, the value of omega, this omega will also rotate with one rotation per second. So within 1 second it will go from this position and come back to this position. So whatever is the angular velocity of the ship, same is the angular velocity of precision. This much you understood? Okay. Now the questions become fairly simple. If the ship is moving with velocity v, v is nothing but omega dash into r. V is omega dash into r. Okay. Or omega dash is equals to v by r. Now if I want to find out the, what do I need to find out? Find the moment of gyroscopic forces. Okay. Moment of gyroscopic forces, that means torque. Torque is equals to I omega dash cross omega. What is the angle between omega and omega dash? Omega is towards you. A vector that is coming to, vector that is going away from you, not towards you. A vector that is going away from you. Angle between omega dash and omega is always 90. Okay. So torque is nothing but moment of inertia of the ship into omega dash is nothing but v by r into omega. Okay. So as soon as you plug in the values, you get your answer. Acha. One more thing. Okay. This rotation or omega dash, sorry, this omega is given as 300 rpm. How do I convert 300 rpm to radians per second? Okay. So 300 rpm is nothing but 300 into 2 pi radians per minute into 60. So whatever n rpm is given, suppose n rpm is nothing but into 2 pi by 60, will get in radians per second. Understood? So instead of applying omega, we'll write omega as 2 pi n by 60. Now plug in the values and get your answer. Okay. Now this question is same as previous problem. Okay, the ship problem. Suppose this is a train. Okay, and this is the wheels of the train. Okay, and I'm looking from this train from the helicopter. Okay, from the sky. Okay, now this train is moving in a circular orbit. Okay, fair enough. Okay, so now there is a turbine inside this train that is spinning in the same direction as the wheel. Okay, that means if the wheels are spinning clockwise, the turbines are also spinning clockwise. So the angular velocity of the turbine would be in this direction. Okay, now when the train reaches out here, okay, suppose let me draw this diagram. Okay, let me draw this entire diagram. Okay, when the train reaches out here, okay, out here. Wait a minute. Array, see, when the train reaches out here, okay, the angular velocity would be in this direction, isn't it? Similarly, when the train reaches out here, but the copy function is when the train reaches out here, the angular velocity would be in this direction. Okay. Similarly, when the train reaches out here, the angular velocity is in this direction, isn't it? So you're seeing that the angular velocity vector is also rotating, isn't it? First in this direction, then in this direction, then in this direction, then in this direction. Okay. So with what velocity is the angular velocity rotating? Omega p. Same as the angular velocity of this train about this track. Okay. So torque is nothing but I, moment of inertia of the turbine, into omega p cross omega. Okay, and omega p is nothing but v by r. Okay, v is given velocity. What is the velocity? Yeah, v is given, convert that into meter per second. R is given. R is nothing but radius of the track. Okay, radius. What is the radius of the track? Whose parallax is the moment of inertia relative. Find the additional torque. Move radius of the track. Okay, 250 meter. Understood? Now we found out that torque. Omega is also given. Omega is given in RPM. So in order to convert RPM, you have to convert n into 2 pi by 60. All that is fair and fine. Okay. Now you have to understand the important concept. Okay. At what direction is the torque? See, torque out here in this position will be in this direction. Okay. Torque out here would be in this direction. Torque out here would be in this direction. Torque out here would be in this direction. See, this torque is trying to rotate the angular velocity, or this torque is trying to change the angular velocity vector. Same like circular motion. In circular motion, what does the centripetal force do? So centripetal acceleration do. Centripetal acceleration tries to change the direction of velocity vector. Similarly, gyroscopic torque out here changes the direction of angular velocity vector. Okay, so this is our concept out here. Fair and fine. Now we'll just see the same railroad from side view. That means I'm standing on the ground and seeing the same railroad. Okay, these are the wheels. Okay, this is a turbine. The angular velocity of the turbine is towards you. Okay, this is omega, and this will keep changing as the thing rotates. And in which direction is the torque? See, if I see this diagram out here, okay, the angular velocity is towards you, the wheels are also rotating clockwise, the turbine is also rotating clockwise, okay, with angular velocity omega given out here. The torque is nothing but in this direction, isn't it? Torque is nothing but in this direction. Okay, now if you point your right hand, okay, and see if I draw the diagram of the railroad from behind, just imagine as a bus. Okay, I'm driving the torque from or railroad from behind. Okay, this was the turbine. The angular velocity was in this direction. Okay, now torque is towards you. This is the torque. Now if we use a right hand, this torque this torque is trying to spin the entire thing anti-clockwise direction, isn't it? Okay, so there would be some additional normal reaction force on this left wheel. No, this is trying to topple. The question is asking what is this additional force. Okay, so let the length Okay. The length, the gauge is equals to 1.5 meter. So if I say this length is nothing but 1.5 meter. Okay. So torque is nothing but force out here into length. So if I consider this as the axis, okay, torque is nothing but force into length, which is nothing but I omega p cross omega. And from this formula, if you substitute all the values, v by r, this is nothing but 2 pi n by 60, will get the value of force. Or force is equals to I v by r 2 pi n by 60 divided by L. Okay, so this is the value of torque. Understood? So this is our last question of video 2. So from the next class, we'll start elasticity. Okay, elasticity from video 2.